Okay, so let's start. Ladies and gentlemen, let's continue with chapter 11 out of the textbook of Cengel and Ghajar. Chapter 11 is where many of the work that we've already done is getting together, and is sort of my favorite chapter. And that is on heat exchangers. So let's start with heat exchangers in terms of a definition. In many cases you'll see HX in literature, and that is just the short version for heat exchangers. So the definition of a heat exchanger is something that facilitates the exchange of heat. Facilitates the change of heat, and it is between two streams. Between two streams at different temperatures. And keeping them from mixing. So it says two streams at different temperatures, heat transfer between them, however they shouldn't mix. In the previous chapters, specifically in chapter 8 or 7, I think, it was very important for us to look at the cases of a constant wall temperature and a constant heat flux. Okay. However, in those cases we had a wall which was at a certain temperature, maybe Ts, okay, and then we had a stream which was the fluid. So there's the fluid, and that was the wall. The constant heat flux, we also had the temperature of the wall doing something like that, and the temperature of the fluid increasing linearly. What is different with that work and this work is that there were never two streams. It was always just a wall. Okay, very important. So that is what's going to be the difference. With this, we've also seen that it is better to use the LMTD method. It is more accurate. And if you're going to try the LMTD here, you're going to see it doesn't work. Okay. So if you want to try and apply the LMTD, then you're going to get, maybe this temperature difference is 10, and then that temperature difference is also going to be 10. So with LMTD, you're going to get this temperature difference minus that one is 0, divided by the ln of 0 divided by 0. So you will immediately see it can't work. So what I would recommend is always try the LMTD in any case, in previous cases. And if you get to this, you're going to see it doesn't work. And then you use just the temperature difference. Right, now there are different types of heat exchangers, and we are going to discuss them shortly, and I'm just going to discuss some of the most important ones. Definitely not all of them. So the simplest type is called the tube-in-tube heat exchangers, and with that we normally have one circular tube inside another circular tube, where now I'm going to use the red chalk and the blue chalk to identify the hot stream flowing through there. Okay, so that is the hot stream. And in the annulus we will get the cold stream. Like that. So that is the temperature of the cold stream. And this is called a parallel flow heat exchanger. Parallel flow heat exchanger. And if we look at what happens with the temperature behaviors, the temperature as a function of X, and this is the length L of the heat exchanger, then typically the cold fluid would of course increase in temperature, while the hot fluid is going to decrease in temperature. Okay. You can also put the hot fluid in the annulus and the cold fluid on the inside, it doesn't matter. Normally, we have insulation material there on the outside to prevent heat losses. So from a losses point of view, and that doesn't mean it is a rule and that is what always will happen, it would be better to have the warmer stream on the inside, because then the temperature there will be lower than the case where you had the hot stream on the outside, so the losses to the environment would just be less. Okay, so that is the parallel flow heat exchanger. Then we have the opposite. The parallel flow heat exchanger is not being used a lot, and later on you'll see why, because it is not as effective as the parallel flow one. If that is the hot stream, TH, then that is the annulus, and what we now have is that the flow in the annulus flows in the opposite direction. So that is the blue. And if we plot the temperature differences as a function of x, and that is the length L of the heat exchanger, then the behavior of the temperature streams is going to be different. Typically, the hot temperature is going to decrease like that, while the cold fluid temperature is going to do something like that. So if you just look at the two graphs, so this is called the counterflow. The counterflow heat exchanger. So if you just look at the graphs, you will see that for the parallel flow heat exchanger, here at the inlet, the temperature difference is very high, which means that the heat transfer rate would be very high. But as the flow goes downstream, the temperature difference just becomes smaller and smaller, and the heat transfer rate will therefore become smaller and smaller. While with the parallel flow one, we can see that it has a delta T all the time. Of course, this one can't go higher than that, because that is the inlet temperature, and that one can't go lower than that point there. That would be for an infinite long heat exchanger. Now, heat exchangers is also defined in terms of a so-called compactness factor, which is called beta, which is the area density. Now, it's not all heat exchangers which that this definition is being used for. It is typically being used for specifically compact heat exchangers where size is very, very important. And the definition of that is that it would be the heat transfer surface area divided by the volume, by its volume. So how much heat transfer area is available divided by the volume of the heat exchanger. Now, if beta is considered is 700 and higher, then it is considered as a compact heat exchanger. Okay. A car radiator is approximately 1000. That is something that we want to have to be compact. Size is very important. If it is too big, then you need more area, more volume in the car. The smaller it is, in many cases also the lighter it will be. And the heat exchanger with the highest value, now I've got a mistake here on my notes. Let me just check. Yeah. So other values of compactness, just to give you an idea, is value of car radiator is 1,000. A glass ceramic gas turbine heat exchanger is about 6,000. The regenerator of a Stirling engine is 15,000. And the highest compact factor that we have is 20,000. And who of you can guess what that is for? That is for the human lung. Your human lung is the most compact heat exchanger that there is. What does it mean? A value of 20,000 means 20,000 square meters per cubic meter. Surface area for heat transfer. Now your lungs are not 1 cubic meter in size, but let's suppose it is 0.1 cubic meters. I don't know if that's accurate. Then it would mean it is 2,000 square meters of surface area that your lung has for heat transfer. That is why it is such an effective heat exchanger. Now, in terms of, let's call it a rule of thumb. Normally, if we've got a liquid and a gas, and we need to have heat transfer between them, then normally, not always, there will be fins on the gas side. There will be fins on the gas side. How is that being done? Well, you can just go and look at the condensers and evaporators of air conditioners. They've got all these tubes like this. And through them, the liquid will flow, either condensing or evaporating. And then typically there will be fins which are connected to all these tubes, typically in that direction. So there's the fins. And another type of compact heat exchanger is the printed circuit. Printed circuit heat exchanger, and that's going to be too complicated for me to try to draw it for you, so I'm going to show you a short video. If I okay, I hope this thing plays. Let's see. Okay, so this is a Alfa Laval printed circuit heat exchanger. There you can see typically how it looks like. That would be typically an inlet and an outlet for the one stream, and there's the inlet for the other stream, and then at the back there would be the inlet outlet for the other stream, in and outlet for all of them. That is typically how you take them apart. Okay, what we're going to concentrate on is what happens there in that part, the plate back. And just so that you can see how compact it is, that's typically how it looks like. Lots of small circuits, and in the circuits there are small devices on the geometry which will typically increase the turbulence. Okay, now the previous slide that you've seen would typically be the cold fluid, and that would be the hot fluid. Very complicated to manufacture, to put together, to ensure that there's no leaking between all of them. That would be in this case the hot fluid. And you'll see it will change direction, so it will move in a lateral direction. In many cases, freezing and clogging is a problem. Clogging because of freezing, and they have all lots of tricks, as you can see, trying to prevent that. Okay. Okay, so there you see the car radiator. Photo is not that clear, but I think most of you have seen it. Okay, there it is. And those heat exchangers, we will get to it just now. Right, now with the next type of heat exchanger is different than in these cases. In these cases, you could see the flow is either in the same direction, parallel flow or counter flow. However, you can, okay, so the printed circuit heat exchanger, it's the video. It would be too complicated for me to try to generate that types of heat exchangers. The next type is the cross flow. Cross flow heat exchanger. With the cross flow heat exchanger, we now have the fluid 1 going in this direction, and then perpendicular to it we will have fluid 2. And with these types of heat exchangers we can get what we call an unmixed configuration. Unmixed or mixed. Now, what is the difference between the two? Well, I'm going to try to draw it for you. This is now the tubes through which fluid 1 will flow. So that's fluid 1. And what we have here is plates, typically like that. Lots of them, normally quite close to each other, a few millimeters. And then fluid 2 will flow through the plates. Okay. And this will be a case of unmixed flow. So mixed or unmixed never has something to do with the two fluids itself mixes. That cannot happen because the definition of a heat exchanger says that the two fluids must never mix. Okay. While for the case where it's mixed, it will be these tubes like that. And now the fluid 2 will just flow like that. Fluid 2, and that would be fluid 1. So this would be the case of mixed flow. Why? Because it mixes in the transverse direction. While in this case, the fluid flow cannot move into a transverse direction. It is being forced to flow along one path. Okay. In this case, it can flow a little bit into a transverse direction. Okay. Now, most small types of heat exchangers, 1 kilowatt and smaller, 2, 3, 5, 10 kilowatts, 20, 30, are these types of heat exchangers. The heat exchanger which is used most in industry for industrial applications industrial applications. Is called the shell and tube heat exchanger. Shell and tube heat exchanger. So this is the most common type of heat exchanger. But if I say that, then I mean that the heat transfer rates that we're talking of are normally in hundreds of kilowatts. So it's not the type of heat exchanger you're going to get into your car, in a fridge, the freezer, in a domestic or a commercial heat exchanger system. This is for hundreds of kilowatts. So for this building, for example, you will have a shell and tube type of heat exchanger, where the water which flows to all the units are being cooled in the shell and tube heat exchanger. So it is for big applications, normally very heavy. You also wouldn't get it on an aeroplane or anything like that. And how it works is like this. You have a shell, that's where the name comes from. So this is the shell, it looks like that. And there will be an inlet for fluid 1. And there will be an outlet. Fluid 1. And in it, here we will have a header. Let's rather put it here, on that side, like that. There and there, typically like that. And in here, we will get fluid 2 coming in like that. And there also, let's rather make the inlet there for fluid 2, and then it should go out there, so that it is sort of in a counterflow direction. Here will be fluid 1, or fluid 2, and here we will have a tube like that. And this tube would go through typically like that. And I'm just going to draw 3 of them so that you can see the concept. Let me see if I can put some color also in it. So let's suppose that is fluid 2. Then fluid 2 will go through there, will go out there, typically like that. So there, then out there. Okay. Fluid 1 will now be on the outside in the shell, and to make things a little bit interesting, we will have some baffle plates in there, typically like that. So it means that this flow can go into the shell like that, and then it needs to flow in a downwards direction, that direction, and then it has to be forced with the baffle to go up again. So let's suppose here's the other baffle like that. We'll force it like that, and then again like that, and out again. So all with baffle plates. So that is the shell and tube. Obviously my sketch isn't that good, but there you can see the principle much better sketch of the principle. Okay? Do you all understand it? Okay. Now you can start doing very interesting things where we start talking of a one shell pass and a one tube pass or two tube passes and two shell pass heat exchanger. And now you're going to ask me, what is this? Well, this would now be a one shell pass heat exchanger. One shell pass and a one tube pass. And schematically, I'm going to show it to you like this. So if this is the shell, this is the shell. Now you can have the cases where, let's suppose that was fluid 1, and that was fluid 1. Okay. Now you can have the tube where it would actually do something like that. All the fluid wouldn't go out into the baffle. It would typically, fluid 1 will go in there, and fluid 1 would exit there. And what we have here is one shell, but a two tube pass heat exchanger. A one shell pass and a two tube pass heat exchanger. The next, okay, so you can get a one shell and one shell pass and a four tube pass heat exchanger. A four tube pass heat exchanger, so that is the one shell. One shell and a four tube pass heat exchanger. Four tube passes would mean 1, 2, 3, 4 going out. A four tube pass heat exchanger. Now we can get to a two shell and a three shell heat exchanger. And that looks like that. The shell now can be divided into two parts. I'd rather do it like this. That is the shell. Then it is being sort of divided into two. And the fluid 1 will go in there. Fluid 1 will exit there. So you can see it will go in there and it will go out there. And that is in the annulus side. Then the tubes can do something like this. 1, 2, 3, 4. Fluid 2 and fluid 2 going out. Okay. So this is now a two shell pass heat exchanger and a four tube pass heat exchanger. Okay. The next type of heat exchanger is called a plate and frame heat exchanger. It's also a very compact type of heat exchanger where we make use of lots of plates next to each other. I'm going to draw them a little bit away from each other. So lots of plates, 20, 30, 40 of these plates. And then we will have fluid 1 going through there. It will exit there, and then it will Okay, I'm going to try to draw it in blue. So it will go through there, and then it's going to skip one, and then it's going to go back through there, between those two. Okay. While the red fluid will go in there, it will follow that path, and then it will go through there. So always between two plates, you will have a hot side and a cold side. And these plates can also be manufactured to have very interesting geometries. So it's typically not a flat plate like this, it is a plate looking like that. And at the same time, if you look at the plate from the front, there are the 4 holes for where it would come in. It will have typically it would be bent like that. All different types of orientations, geometries, etc. Typically these heat exchangers are very compact. What is very nice about them is as your heat duty would increase or decrease, you can usually just add some more plates or take out plates. However, normally they cannot take very high pressures, so it's typically being used. A good example is in the process industry, where you've got milk and hot water and cold water, and maybe you want to cool the milk a little bit with a few degrees Celsius, not high pressures, and very compact and easy type of heat exchanger to use. Specifically in the milk industry and the food industry, you can then, after you've done your processes for the day, you can actually take it apart and you can clean the heat exchanger and you can put it back again. Okay. The last sort of category of heat exchanger, before we get to the mathematics, would be the regenerative heat exchanger. The regenerative heat exchanger. And in that heat exchanger, we would actually have a porous media. Porous media. And the porous media would typically be a ceramic wire. And at T equals 0, we will have fluid 1 going through the porous media. Let's suppose this fluid is a hot fluid. Then it would increase the temperature, it would start storing all its heat there. Then at T equal delta, okay, you will have fluid 2 going through the same mesh. And that is how you can transfer the heat from the one fluid to the other fluid. These types of heat exchangers are specifically now being investigated for concentrated solar plants. So as you know, concentrated solar plants, they make use of lots of mirrors. There would be a tower with a cavity receiver, and then you have all these mirrors that would actually concentrate their sunlight on this heat exchanger, the cavity receiver. And during the day, you can capture all this heat. But now at night, there's no sunlight, but we need electricity during the night. So in these types of plants, lots of investigations are being done now to, while the sun is shining, to also store some of the heat. And this is a typical type of heat exchanger that can be used for that. In South Africa, excuse me, specifically a lot of work is being done now to see if rock can be used. Why rock? Well, the reason for rock is that it is very cheap, and then also specifically in South Africa, the CSP plants, or the best places where you can put CSP plants, is in the Northern Cape. It's in many cases desert type of area, and there are lots of rocks. So the rocks are being investigated as possibilities. Obviously you need to open up a huge hole, put the rocks in there, and during the day store the heat there, and then at night when the rocks are all 1100 degrees Celsius, something like that. I cannot remember the temperature. Then you can remove the heat again and you can still drive the power plant. So this is one type of configuration, but you can also have configurations where the two fluids go through the porous media at exactly the same time. And normally this is then done in the form of a type of a wheel which is being rotated at a small velocity. And then we will have fluid 1 that would typically heat this porous media, fluid 1, and there will be fluid 2, and they do not mix. So here it will heat it, and the heated porous media will then go into the cold stream, and then the heat transfer will occur on the cold side. Okay, so that is actually called the dynamic type, and this is called the static type of regenerative types of heat exchangers. Right, that is just now a little bit of background. In your textbook, you'll be able to see much more beautiful or better pictures than that I have shown you. So let's look at the importance of how can we actually now go and apply all the work that we've done on these different types of geometries. What should be remembered before we actually now start with all the mathematics is I just want to take you back to your thermodynamics. In your thermodynamics, if that is a TS diagram, I hope you remember that this is a superheated area, and that is the saturated vapor point, and that is the saturated liquid point, and that is a line of constant pressure. So condensation would typically be, now let's suppose this fluid or gas has been superheated up to this point. If we would have that in a heat exchanger, any of these types of heat exchangers, and this is now the hot side, and it is being cooled, what you will see is it's going to move down there. Okay. What happens with the temperature when it moves down there? The temperature decreases, just like I've shown typically for the parallel flow heat exchanger and the counterflow heat exchanger. However, and that is now the big however, is the moment condensation occurs, the temperature is going to remain constant. There's not going to be a change in temperature. So if we go back to these types of heat exchangers here, let's suppose the parallel flow heat exchanger, if this is now the hot side, we will have something like that happening. And as you can see, the difference is obviously the heat transfer rate. So it will mean that the best types of heat exchangers, the most efficient types of heat exchangers would be heat exchangers where on the one side you have condensation, okay, or boiling or evaporation. So that would be for condensation. For boiling, I'm just going to obviously, yeah, let's rather draw it there. So for boiling, it's going to be there like that. And again, the temperature is going to remain constant. If you've got a vapor compression system, again, typically like that, that's going to be the compressor, that's going to be your condenser, you're going to do a little bit of subcooling there, and then you're going to go through the expansion valve, and again, there you're going to have your condensation, there's going to be evaporation. However, what is important is during those two processes and during the process of boiling, the temperature remains constant. And if you can get the temperature to remain constant of your heat exchanger, you always have a very effective type of heat exchanger. So let's introduce what we've actually already know, but we're going to start applying it now to heat exchangers. Okay, let's suppose we have a part of a tube, and I'm just going to enlarge it now like that. Okay, so that's part of a circular tube, and that is the wall thickness. Or it can be a wall like this. Okay. And let's suppose that is the temperature on the inside, and that is the temperature on the outside. The same here, there's a temperature there on the inside, a temperature on the outside. What we will see is that if we go and plot the temperature as a function of X or R, let's first do it for this one. If that is the temperature on the inside, and if we go and measure the temperature there, it is going to be lower. So typically, that is what's going to happen with the temperature. Then we've got the temperature over the wall. Again, something like that. Excuse me. And then lastly, we're going to have the temperature difference like that. So that is T0, cold fluid. And the same with this case where we've got a wall like that. So in this case, a circular wall. In that case, a wall like that. Ti, that is T0. Temperature differences doing something like that. How are we going to describe it, and what will be the tools that we're going to use for it? Well, I hope that you can still remember from chapters 1 to 3 that this is all about the resistance of different elements. Okay. Oops. Okay, I'm going to take this thing and just make it a little bit larger. Like that. Ti and T0. Okay. This is going to be the resistance on the inside, that's the resistance on the outside, and this is going to be the resistance of the wall. This is the resistance of the wall, the resistance on the inside, and the resistance on the outside. The resistance on the inside, I hope you can remember, is equal to 1 divided by the heat transfer coefficient on the inside, multiplied by the surface area on the inside. The resistance of the wall is going to be the ln d0 divided by di divided by 2 pi kl, where that would be the diameter on the inside and that would be the diameter on the outside. Or, if it is a wall like this, it will be equal to x k multiplied by the area of the wall. The heat transfer coefficient of this resistance would be equal to 1 divided by the heat transfer coefficient on the outside multiplied by the area on the outside. Therefore, the total resistance, okay, and I'm just going to use this case now. This case is just where we've got this term is being replaced by that term. Okay. So the total resistance is equal to 1 divided by the heat transfer coefficient on the inside, multiplied by the area on the inside, plus the ln of the diameter ratio divided by 2 pi kl, plus the resistance on the outside, which is equal to 1 divided by the heat transfer coefficient multiplied by the area on the outside. Of course, the area on the inside would be equal to pi multiplied by the diameter on the inside, multiplied by the length of this tube, okay, or the heat exchanger, while on the outside it would be equal to pi d0 multiplied by L. And in general, what you've done in chapter 3 last year is to say that the heat transfer rate is equal to delta T divided by the total resistance. Okay. Now, just like that, we are going to say that for heat exchangers, heat transfer rate is equal to the overall heat transfer coefficient multiplied by the surface area multiplied by LMTD. Okay, now what is this overall heat transfer coefficient? If you use this and you look at this R total and you go and play around with it, then you will see that 1 divided by the resistance is equal to U multiplied by the area. And which is something which is now a little bit confusing is also that we can say that the heat transfer rate is equal to U multiplied by one or other surface area multiplied by LMTD is equal to the overall heat transfer coefficient on the inside multiplied by the area on the inside multiplied by the LMTD is equal to the overall heat transfer coefficient on the outside, the area on the outside, and LMTD on the outside. And this big U is known as the overall heat transfer coefficient. Exactly the same units as previously for a heat transfer coefficient. Watt per square meter degree Celsius. Thus, in general, we can actually go and write 1 divided by the overall heat transfer coefficient multiplied by the surface area is equal to 1 divided by the overall heat transfer coefficient inside, area inside, is equal to 1 divided by the overall heat transfer coefficient outside, area outside, is equal to R total, is equal to 1 divided by the heat transfer coefficient the inside, area on the inside, plus the resistance of the wall, plus 1 divided by the heat transfer coefficient on the outside and the area on the outside. Okay, so note that the heat transfer coefficient on the inside multiplied by the area on the inside is equal to the heat transfer coefficient on the outside multiplied by the area on the outside. But that doesn't mean that the heat transfer coefficient on the inside is equal to the heat transfer coefficient on the outside. Why? Because normally the outside area is going to be larger than the inside area. There's a special case, which is this case, where this area and that area is exactly the same. Then the overall heat transfer coefficient would be the same. Okay. Now why? So the overall heat transfer coefficient is meaningless except if the area is defined. Very important. U is meaningless except if area is defined. Okay. So where are we going to? We are moving into the direction where we want to take a very complicated heat exchanger, something like this, with maybe 100 or 200 tubes. We do not want to go and calculate the heat transfer coefficient of every one of them, and then the heat transfer coefficient of this annulus. we want to get everything into one value. However, if we get it in a one value, then we have to say it is based on the outside area of those tubes, the inside area of those tubes, or maybe the outside area of the inside area of the shell. But we have to say, because if we've got one U, then it is very easy for people to do the calculations for a heat exchanger. If heat exchangers companies wants to sell the heat exchangers, it's easier to give one value. And then you can use the one value to do calculations with. And I'm going to show you some examples of that in the next lecture. Ladies and gentlemen, thank you very much.